Welcome! In today's session, we will explore an interesting coding problem: rearrange words in a sentence. This problem challenges us to manipulate and reorder words in a sentence based on specific criteria. We'll break down the problem, analyze potential approaches, and evaluate their efficiency. Let's dive in. In this problem, you'll be working with a sentence, which is essentially a string consisting of space-separated words. The goal is to rearrange these words according to three specific rules. First, the words need to be ordered based on their lengths in ascending order. If two or more words have the same length, they should remain in the same relative order as they appear in the original sentence. Second, the first word in the resulting sentence must be capitalized, and third, all other words should be in lowercase. After applying these transformations, you'll return the rearranged sentence as a single string. The input format for this problem is a single string, which represents the original sentence, and the output is also a single string, representing the transformed sentence. Let's look at some examples to better understand these requirements. Consider the first example, where the input sentence is LeetCode is cool. The words in this sentence are LeetCode, is, and cool, and their respective lengths are 8, 2, and 4. To rearrange them, we first sort the words by their lengths in ascending order. This gives us the order is, cool, and LeetCode. According to the rules, the first word in the rearranged sentence should be capitalized, and the rest should be lowercase. So, the final output is cool LeetCode. This example demonstrates how the words are reordered based on their lengths while adhering to the capitalization requirements. Now, let's take a look at the second example, where the input sentence is keep calm and code on. The words in this sentence are keep, calm, and code, and on, with lengths of 4, 4, 3, 4, and 2, respectively. After sorting these words by length, the order becomes on, and, keep, calm, and code. The first word, on, is capitalized, and the others are converted to lowercase. As a result, the output becomes on and keep calm code. This example highlights how ties in word lengths are handled while maintaining the relative order of words with the same length. For the third example, the input sentence is to be or not to be, that is the question. Breaking it down, the words are to be or not to be, that is the and question, with lengths of 2, 2, 2, 3, 2, 2, 4, 2, 3, and 8, respectively. When sorted by length, we get the order to be or to be not is the, that, and question. Capitalizing the first word and converting the rest to lowercase gives us the output to be or to be not is the that question. This example further illustrates how the rules are applied even with longer sentences and varying word lengths. Finally, let's touch on some important constraints and edge cases. The sentence will only contain English letters and spaces, with no leading or trailing spaces, and at least one word will always be present. The input length will not exceed 10,000 characters. For edge cases, if the sentence contains just one word, the output remains the same, but the first letter of the word must still be capitalized. If all words have the same length, their original order must be preserved. Additionally, if the input sentence has mixed capitalization, such as this is a test, the output must follow the rules, with only the first word capitalized and all others in lowercase. These considerations ensure your solution is robust and handles all scenarios correctly. To approach this problem, we can start with a straightforward brute force method. The intuition here is to split the input sentence into individual words, sort them based on their lengths, and then reassemble those words into a new sentence. Specifically, we can break this down into 4 steps. First, we tokenize the sentence into an array of words using Python split function. Then, we sort these words by their length using the sorted function with a custom key. Once sorted, we reconstruct the sentence by joining the words with spaces using the join function. Finally, we adjust the capitalization so that the first word is uppercase and the rest of the sentence is lowercase, ensuring the output matches the expected format. It's important to note that sorting the words by their lengths is the most critical operation here. While this approach is simple and easy to implement, it forms the foundation for further optimizations. Now, let's analyze the complexity and trade-offs of the brute force approach. Since sorting is the dominant operation, the time complexity of this method is O, n log n, where n is the number of words in the sentence. The simplicity of this approach is a major advantage. It's quick to implement and works for most cases. However, there's a trade-off. This method does not guarantee stability when sorting words of the same length. Stability refers to preserving the relative order of words with equal length as they appeared in the original sentence, which can lead to incorrect outputs in certain edge cases. To address this, we can turn to an optimized approach. The optimized method builds on the brute force idea but introduces stable sorting by leveraging Python's sorted function, which is inherently stable. The key insight here is to pair each word with its original index, allowing us to sort primarily by length while breaking ties using the original index. This ensures that words of the same length maintain their original order, resulting in a more robust solution. Let's break down the steps of the optimized approach in more detail. First, we tokenize the sentence into words just as before. Next, we create tuples for each word, where each tuple contains the word's length, its original index, and the word itself. This structure allows us to sort the words not only by length but also by their indices to handle ties. Once sorted, we extract the words from these tuples and reassemble them into a sentence using the join function. Finally, we fix the capitalization by making the first word uppercase and the rest lowercase, just like in the brute force approach. The time complexity remains n log n, since sorting still dominates, but this strategy guarantees correctness by ensuring stable sorting. While slightly more complex than the brute force method, this approach is preferred for its reliability in edge cases. By incorporating the original indices into the sorting logic, we achieve a robust solution without significantly increasing complexity. The optimized approach stands out as the best choice for several reasons. First, it ensures correctness by guaranteeing stability in sorting, which is critical for handling words with equal lengths. Second, it is efficient, sharing the same n log n time complexity as the brute force method, but with added robustness. Finally, it remains simple to implement, requiring only minor modifications to the brute force approach. This balance of simplicity, correctness, and efficiency makes the optimized approach the most reliable solution for this problem. By leveraging Python's stable sorting and incorporating the original indices of words, we ensure the output meets all requirements while minimizing the risk of errors in edge cases. This makes the optimized approach not only practical but also the most elegant solution to the problem at hand. The goal of this problem is to take an input sentence and rearrange its words so that they are sorted by length in ascending order. Additionally, if two words have the same length, they should appear in the same order as they do in the original sentence. This is called maintaining the stability of the sort. To achieve this, we start by accepting the input sentence as a string. For example, the input sorting sentences by word length is treated as a single string. The next step is to break this sentence into individual words using a string splitting function. This creates a list of words, such as sorting sentences by word length. Splitting the sentence into words is essential because it allows us to treat each word as a separate element, which is critical for sorting them effectively later on. Now that we have a list of words, the next step is to sort them based on their lengths. A stable sorting algorithm is used here to ensure that words of the same length retain their original order. For example, consider the words sorting sentences by word and length. Their lengths are 7, 9, 2, 4, and 6, respectively. When we sort them by length, the result is by word length sorting sentences. Stability in sorting ensures that if two words have the same length, like sorting and sentences, their relative order remains unchanged. Once the words are sorted, the final step is to reconstruct the sentence. We do this by joining the sorted words back together using spaces as separators. This gives us the output string by word length sorting sentences. We also need to handle edge cases, such as when the input is an empty string. In that scenario, we simply return an empty string as the output. For other edge cases, if the input contains only a single word, we return it unchanged since there's nothing to sort. If the sentence includes punctuation, we need to decide whether to treat it as part of the word or to remove it, depending on the requirements. A key insight for this problem is the importance of using a stable sorting algorithm, which ensures that the relative order of words with the same length is preserved. Python's built-in sorted function, which uses timsort, is stable and works well for this purpose. When analyzing the complexity, we see that splitting the input string into words takes n, where n is the number of characters. Sorting the words based on their lengths takes O, k asterisk log, k, where k is the number of words. Finally, joining the sorted words to form the output string takes O, n. Therefore, the overall complexity is O, n plus k asterisk log, k. Data flow is straightforward. The input string is split into a list of words, which is sorted, and then joined to produce the output string. To implement this solution efficiently, we rely on two key data structures, lists and strings. The list is used to store the words after splitting the sentence. Lists are ideal for this task because they allow random access and can be sorted efficiently. The final output is a string, which is created by joining the sorted words together. Although strings are immutable, Python's join operation is optimized for creating new strings efficiently. Key operations in this algorithm include splitting the sentence into words, sorting the list of words, and joining the sorted words into a single string. To optimize the process further, we can use Python's built-in sort function with the key argument set to the length of the words. This eliminates the need for unnecessary computations, such as repeatedly calculating word lengths during comparisons. Finally, handling edge cases explicitly, like empty input or single-word sentences, ensures that the solution is robust and avoids unexpected errors in real-world scenarios. This code defines a solution for LeetCode problem number 1451, rearrange words in a sentence. First, the arrange words function takes the input sentence as a string. It splits the sentence into words using the split method, which separates the string into a list of individual words. The first word's capitalization is adjusted to lowercase to ensure consistent formatting during the sorting process. Next, the words are sorted based on their lengths using Python's sort method, with key equals len ensuring that words are ordered by their length. This sorting is stable, meaning words of the same length retain their original order. Once sorted, the first word in the modified list is capitalized to maintain the sentence's proper formatting. Finally, the sorted list of words is joined back into a single string using the join method, with spaces between words. The resulting string is returned as the output, representing the words rearranged by length while preserving sentence structure. Here, we begin the implementation of the solution by importing necessary packages, such as java.util, to work with collections and utilities. Inside the solution class, we define the arrangeWords method, which takes a sentence as input. First, we split the sentence into individual words using the split method, which creates an array of words. Then, we convert the first word to lowercase to ensure uniformity during processing. To maintain the stability of words with the same length while sorting, we create a list of pair objects. Each pair consists of a word and its original index in the sentence. We iterate through the words array, populate the list with these pairs, and prepare them for sorting. The sorting logic is then implemented using a comparator. It first compares the lengths of the words, and if two words have the same length, their original indices are compared to preserve the order. This ensures that the sorting is stable while achieving the desired arrangement by word length. Finally, we initialize a string builder to help reconstruct the sentence from the sorted list of pairs. We continue by appending each word from the sorted list of pairs to the string builder, ensuring that the words are added in the correct order. Once the sentence is reconstructed, we handle the case formatting. The first letter of the rearranged sentence is capitalized, and any trailing spaces are removed using the trim method. This step ensures the output adheres to the expected sentence format. The rearranged sentence is stored in the variable rearrange text and returned as the final result. Additionally, we define a helper class called pair within the solution. This class contains two fields, word, which stores the word itself, and index, which keeps track of the original position of the word in the input sentence. This structure allows us to efficiently pair words with their indices and sort them while maintaining stability. By the end of this implementation, the input sentence is rearranged based on word length, with ties resolved by their original order, and the result is returned as a properly formatted string. Let's walk through the first example, where the input sentence is LeetCode is awesome. We start by splitting the text into a list of words. This gives us the list, LeetCode is awesome. Next, we convert the first word, LeetCode, to lowercase, resulting in LeetCode is awesome. Now, we sort the words by their length. Python's sort function is stable, which means that words of the same length will remain in the order they appeared originally. After sorting, we get is awesome LeetCode. Once sorted, we capitalize the first word, so is becomes is, giving us the list is awesome LeetCode. Finally, we join these words back together into a single string, resulting in the output is awesome LeetCode. This demonstrates how we rearrange the words in the sentence while adhering to the requirements. Now, let's look at a simpler case with a single word input, hello. First, we split the input into a list, which gives us hello. Then, we convert the first word, hello, to lowercase, resulting in hello. Since there's only one word, sorting doesn't change the list, it stays as hello. After this, we capitalize the first word, so hello becomes hello, and the list becomes hello. Finally, we join the words back together, which results in the output hello. This example highlights how the solution handles inputs with just one word while preserving the expected transformations. Now consider an example where all the words have either the same or very similar lengths, such as the input, my cat is fat. First, the input string is split into a list of words, giving us, my cat is fat. The first word, my, is then converted to lowercase, resulting in, my cat is fat. Next, we sort the words by their length. Since all words are either 2 or 3 characters long, the sorting process maintains the relative order of words with the same length. After sorting, we get, my, is, cat, fat. Following this, the first word in the sorted list, my, is capitalized, giving us, my, is, cat, fat. Finally, the words are joined back into a single string to produce the result sentence, my is cat fat. This illustrates how the solution maintains stable sorting while rearranging words of similar lengths. To analyze the time complexity of our solution to problem 1451, let's break down the process step by step. First, splitting the input sentence into words using the split function takes n time, where n represents the total length of the input string. This is because each character in the string is examined during the splitting process. Next, converting the first word to lowercase using words 0 to lower takes k, where k is the length of the first word. Since k is always less than or equal to n, this operation is n in the worst case. Now, when we sort the words by their lengths using words.sort, key equals len, the timsort algorithm is applied. Sorting itself has a time complexity of m asterisk log m, where m is the number of words. However, since the key function computes the length of each word, this adds an additional m asterisk k complexity, where k is the average word length. Combining these factors, sorting the words by their length results in a total complexity of m asterisk log m plus m asterisk k. Capitalizing the first word using words 0 capitalize is another important step. This operation, which modifies only the first word, takes k, where k is the length of the first word. Again, in the worst case, this is n. After capitalizing, we join all the words back into a single sentence using .join words. Joining the words requires traversing the total length of all words combined, which takes n time. Now, if we consider all the operations together, the total time complexity is determined by the most expensive step, which is sorting. Let n represent the total length of the input string and m the number of words. The sorting step dominates with a complexity of m asterisk log m plus m asterisk k. Since k, the average word length, can be approximated as n divided by m, this simplifies sorting to m asterisk log m plus n. Adding the linear contributions of the other steps, the overall time complexity becomes n plus m asterisk log m. Now let's examine the space complexity of this solution. First, splitting the sentence into words using text.split creates a list of m words, requiring m space for the list structure. Additionally, the words themselves require n space, as the total length of all words is n. So, the total space required for splitting is n. Sorting the words using the timsort algorithm is done in place, but it may require up to m auxiliary space in the worst case. For capitalization and joining, the operations modify the words in place, but the joining step constructs a new string, which requires n space to store the resulting sentence. When we combine these factors, the dominant space usage comes from storing the list of words in the final rearranged sentence. Thus, the overall space complexity of the solution is n. Finally, let's compare this optimized approach to a potential brute force solution. A naive method might generate all permutations of the words, sort them manually by length, and then join them back into a sentence. However, this would result in a time complexity of O(m) for generating permutations, which becomes infeasible even for small inputs. The space complexity would also be O(m) due to the storage required for all permutations. In contrast, our optimized approach leverages sorting and string manipulation to achieve a time complexity of O(n plus m asterisk log m) and a space complexity of O(n), making it significantly more efficient and scalable. Additionally, the time complexity remains consistent at O(n plus m asterisk log m) regardless of the input structure, as sorting dominates the runtime. This consistency applies to the best, average, and worst cases. Mathematically, sorting's complexity of O(m asterisk log m plus n stems from timsort and key computation, while all other operations are linear and do not impact the overall big O. Therefore, the total time complexity is O(n plus m asterisk log m). When solving this problem, there are several common mistakes you want to avoid. First, ignoring edge cases is a frequent pitfall. For example, if you don't account for empty strings, single-word inputs, or sentences with multiple spaces, your solution might fail in these scenarios. Testing against these edge cases is essential to ensure robustness. Another issue arises with incorrect string splitting. If you don't trim leading or trailing spaces properly, splitting strings like "Hello World" could lead to unexpected results. Be careful to handle these nuances. Additionally, modifying the input string in place can lead to inefficiencies and errors, especially when the problem requires constructing a new output string. Inefficient sorting is another area to watch out for. Failing to handle ties and word lengths, for instance, can lead to unstable results. To address this, use a stable sorting algorithm or include a secondary criterion, such as lexicographical order. Finally, inefficient implementations, like using nested loops or redundant operations, can unnecessarily increase complexity. Aim for an optimized solution, ideally around O(n log n) if sorting is involved. This problem is a great opportunity to demonstrate key problem-solving skills during an interview. It often tests your ability to manipulate strings, so recognizing patterns in tasks like splitting, sorting, and reassembling strings is crucial. Edge case handling is another area interviewers focus on, as it shows the robustness of your solution. Scenarios such as empty input, single words, or special characters are common tests, so make sure to address these explicitly. Time complexity is also important. While an O(n log n) solution involving sorting is acceptable in many cases, it's a good idea to discuss potential optimizations, such as whether sorting can be avoided entirely. Finally, clear communication is essential. Walk your interviewer through your thought process, especially when it comes to choosing sorting criteria and resolving ties and word lengths. This not only helps demonstrate your understanding but also builds confidence in your approach. If you want to deepen your understanding of this problem, exploring related problems can be highly beneficial. For example, LeetCode 151, Reverse Words in a String, focuses on splitting and reversing word order, which overlaps with some of the techniques used here. LeetCode 49, Group Anagrams, involves sorting and grouping strings, which can help you practice sorting-based solutions. Another related problem is LeetCode 937, Reorder Data in Log Files, which tests sorting with multiple criteria, much like handling ties and word lengths here. Lastly, LeetCode 271, Encode and Decode Strings, emphasizes string manipulation and reassembly, a key skill for tackling this problem. As for alternative approaches, consider using counting sort when word lengths are bounded, as it can reduce complexity to O(n), though this comes at the cost of additional space. A two-pointer approach might be used for in-place solutions to partition words by length, but while efficient, this method is less intuitive. Using a custom comparator with a stable sort allows you to handle ties lexicographically, ensuring deterministic outputs. Lastly, though uncommon, dynamic programming could apply in variations where optimizing rearrangement or minimizing some cost function becomes necessary. However, DP is rarely required for the basic form of this problem. Great job! We've successfully tackled the problem rearrange words in a sentence and covered the brute force approach. Remember, string manipulation and sorting are essential tools in your coding toolkit. Stay curious, keep practicing, and I look forward to seeing you in the next session. Thanks for watching. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!